The screen is visible, and am I audible?
Yes, yes.
So let's wait for a while. Let's see if others join. Then we'll start. So we'll start. Eventually, we'll let others join. So you are done with week 2 lectures, right? Am I audible? Hello.
Yes.
Yes. So first we'll try to discuss something. If you are having any difficulty in the week 2 lecture, then we'll go to solving some problems, and yeah, that is what we'll do in this session. And if you have any questions, I have started a mail chain. If you have noticed, I mailed you regarding last week's lecture, because week 1 is pretty straightforward, does not have much. It has a kind of overview, so I did not want to burden you with one more class, but there is already another session, I think. So you already have solved some problems, I guess. So anyways, so I will try to guide you through if you don't understand something in the lecture material, and I'll try to bring you some more problems, and hopefully that will help you in exams or in solving assignments. So all of you who are attending this, all of you enrolled for the exam, or just doing the course by solving assignments and all?
Enrolled for exam.
Enrolled for exam. Others? Okay. Okay. Fine. So yeah. So in week 1 you have already seen that where and in what fields we use CPS. So CPS is a term that we use to describe systems that are controlled using embedded platforms, and where the plant is physical. You know all these things. I'm not going into all these things. So primary components. Primary components are sensors, actuators, and the medium that we use to communicate between the plant and the controller. We will talk about them today. So sensors, actuators, and communication mediums. So start with these sensors that we use. Basically, what are the sensors trying to do? The sensors are basically trying to uh, quantify certain physical phenomena. The plant is being operated by certain physical phenomena, and we are trying to quantify how much it is doing and what it is doing. So to quantify that, to measure its state while the physical phenomena is happening, we use the sensors. So most of the sensors that you will see in this course or in CPS, those are mostly like transducers. Basically, they are converting mechanical energy into electrical energy, so that we can via the electrical signals we can understand and measure from the voltage level or the ampere level, current level. We can understand what is happening and how much value should we consider uh, as its measurement, whatever it's happening. So anyways, so one such example is inertial measurement unit that we have seen. So do you guys are you guys having any problem regarding understanding this? I just want to know. Otherwise, there is no point of wasting time. Anyone, if you have any problems regarding this, then you can ask. If you have noted down while you are listening to the lectures, you can ask some questions. I'll just take you through the slide anyways. So yeah, and it will be helpful if you respond. That will make our session more interactive. Anyways, so yeah, so IMU sensors, initial measurement unit sensors. Basically, where do we see this? We see these in most of the systems nowadays, because all the automotives, all the vehicles that we are trying to make them autonomous. So we are using these sensors so that we can measure. What are the things that we try to measure? So there are basically its position. We obviously try to measure, and measuring its position is not enough. So what do we need? We need to know the velocity along each of the axis, x, y, and z, and that is also not enough. So we need to know the angular velocity along each of the axes. So along each of the axes, if we want to measure the angular velocity, so what are the ways to do so? So there are different sensing units that are used for that. So basically, the idea is simple. So to start with, we'll give you certain examples here. Other than this, there are multiple sensors, and there are multiple different sensor units that are used in actual systems. So if you uh, try to summarize this, then we'll see there are different ways to make sensors. So these sensors that we are talking about, like inertial measurement unit that we are talking about here, so we are going to talk about accelerometer, gyroscope, magnetometer. So all of them will be converting from some mechanical energy to some electrical energy. So when we are converting, consider the accelerometer sensor. So first thing, MEMS, micro electromechanical systems. So why do we use MEMS systems? So they are not that big, so they are not spacious, they don't take much space, and they are easy to make, obviously. And obviously for precision you need to choose the materials very precisely, but they are affordable in terms of space. If you need to have a mobile structure, because most of the CPSs are mobile, if you see, obviously there are CPSs like industrial CPSs which can take larger space. For that there are different kinds of sensors. Mostly if you see, the sensing units are deployed in the remote areas to collect what is the amount of voltage or what is the amount of maybe phase angle. In case of, maybe I am telling, maybe you are talking about smart grid. So in smart grid is a huge CPS, so it's a distributed CPS. There are sensors everywhere in the field. So from those sensors, whatever data we are getting, while we are getting the data, where we are deploying the sensor, that is not a that is not the place where we operate from. So we need to remotely transmit the data that we gather. For that, that sensor unit should be a mobile unit. So maybe we are implementing that in automotives, maybe we are implementing some sensors in case of drones or other any mobile CPS. So there we have to have the sensor in a way, we have to make the sensor in a way so that we can afford the space. So MEMS, micro electromechanical systems, basically helps us in doing that. So in most of the MEMS systems, you will see there will be certain suspended mass that will help us understand the state. So mostly we'll be relying on certain properties of materials. Either they will be based on the capacitance, or they will be based on the resistance, or they will be based on there will be other special phenomena. Based on that also we make certain things. We'll come to that. So basically we call in this case, while we are talking about the accelerometer sensor, so basically they the idea is simple again. When a vehicle or any cyber physical system, it can be our it might not be a cyber physical system as well, it is present in our phone as well. When we try to understand what is a accelerometer, there is a accelerometer sensor in our phone as well, when I am trying to track certain things using our camera maybe. So in other purposes also, when you are seeing maps, we need to know the how, with how much speed we are moving, to measure the speed. So there are application of this in many places. So the idea is basically the direction we are moving towards, in that direction we are letting a suspended mass move. We call it uh, any idea what do we call it? So this is a standard term used in this in such sensor making fields. So this is called basically proof mass or seismic mass. So this is basically a tiny suspended mass that moves in the response to the acceleration. Like when you are moving towards a certain direction, it is also moving, and when you stop, it understands that you are stopping, and based on certain phenomena we'll understand, we'll measure that in how much speed we were moving and we are stopping, with how much force we are braking and stopping. So basically we need to calibrate it first. How do we calibrate it? So basically when a proof mass is moving towards maybe when you are starting a car, so you are starting a car along x-axis. So when you are starting a car along x-axis, when you are in resting position, you can see when the proof mass or seismic mass is suspended and it is not moving, it is attached with certain what should I say, electrodes. So basically between those electrodes you can measure a capacitance. So whatever medium is there it can be designed with different mediums obviously. So you can sense how much capacitance is there between those electrodes. Based on the movement of the proof mass or the seismic mass or suspended mass, when that plate is also moving, the capacitance level is changing. Measuring this capacitance, basically we are finding out with how much speed, with how much acceleration I am speeding up. So when it is resting, I can measure that this is the capacitance value. Obviously the power is constant. With that constant amount of power or the constant amount of voltage, I can measure how much is the capacitance when it is resting. When I am starting to move, so you will understand a certain rise, since the mass will be moving. So now there will be a certain rise in the capacitance. It can be a rise, it can be start reducing also depending on the medium obviously. So basically the distance between the plates will be changing, the medium will be changing, the width of the medium will be changing, and based on the width of the medium the capacitance value will change. Now as the capacitance value is changing, you are understanding basically with what rate that capacitance value is changing. By calibrating that you can understand that your with how much speed you are the vehicle is accelerating. So these things are all calibrated while these sensors are made, and after calibration these are deployed, and then it helps us to understand what is the acceleration of the overall system, and that is measured by the displacement of the obviously the plates, as I said. So this is usually measured using G scale. G scale is basically we know the G value of 9.8 meter per second square. So 1G, if we are calibrating it with 1G, then it means that I am having the acceleration of 9.8 meter per second square. With 2G or 1.5G, accordingly it increases or decreases. So basically it gives me an output with respect to the G value. Okay, so this is one way to do it. And now this is not the only way to do it, that is what I was trying to say. So this is how it is done usually when we see in autonomous vehicles and autonomous drones. Usually these kinds of MEMS accelerometer sensors are implemented. But if you see in other places, in some places piezoelectric sensors are also, materials are also used. Now do you know what are the piezoelectric effect on a material? Anyone?
It converts acceleration or any movement into voltages.
Yes, voltages. Basically, acceleration. It is a vague description. Yeah, you can say that. So basically, what happens is it's a special property of certain materials. We use that those materials in this in making these sensors, and what they do when they are deformed, with high pressure maybe, or by applying certain force, what happens is they change their conductivity. So based on that we can understand that what is the pressure or what is the force applied on that material. By measuring that we can understand what is the acceleration. There are certain materials that those are piezoresistive. So in that case resistance increases by measuring that. Electrical resistance, how much it is increasing as we increase the strain or stress, however it is, we can measure it. So usually those materials are used as a spring. If you see here, we are using the suspended mass and connecting the suspended mass with the electrodes and measuring the displacement of electrodes while the CPS is accelerating towards a certain axis. To measure along different axes, we will obviously deploy multiple electrodes in multiple directions with multiple masses, and maybe we can use it with one mass also. But if there are multiple plates and if we measure in every axis, along every axis, capacitance along every axis for those electrodes, we will get how much acceleration is there along each of the axes. So this is one way of doing it. And if we are using piezoelectric or maybe piezoresistive materials to make such MEMS units, basically those are used in the spring. So obviously as the mass will move, the spring will be stretched, and based on that, if you measure that how much strain we are causing, and based on that you will understand how much voltage, you will understand how much your strain you are causing by measuring the voltage through it or the current through it, if it's photoresistive, piezoresistive. So yeah, measuring that, you'll obviously understand, you can quantify basically that how much with how much acceleration the vehicle is moving and at which direction. So yeah, so this is one way of doing it. Another thing that I started with, how do we understand the angular velocity along each of the axes? So this is something linear. So linear acceleration, for measuring linear accelerations, we use accelerometers. So basically this works on simple Newton's second law, I guess, F equals to m into a. Now if we want to measure the angular velocity or angular acceleration, how do we do that? So for that we use different kinds of sensors, inertial measurement unit sensors. So there are MEMS gyroscope sensor. So gyroscope sensor is one of the sensors that are used in inertial measurement units to measure the angular velocity or angular acceleration, obviously. So yeah, so what is it relies on the Coriolis force. Coriolis force is what? Anyone?
It is just like a centrifugal force, like whenever there is a force that in atmosphere, also when Earth is moving, so
Yes.
the
Basically a
Coriolis forces,
rotating object, when it is rotating
yes, rotating, and then
along a
the
certain
forces
axis.
which is applied on the atmosphere, what we say is Coriolis forces. In
Basically
case
you are
of Earth,
saying Earth's atmosphere, you are saying.
yes, yes, yes.
Yes. What about others? Kunal, Sandeep, are you understanding? Anyways, you can respond, you can ask questions if you want. That will make us, yeah, thank you. If you have questions, use your mic and ask. That will be helpful. Anyways, it's fine. If you are stuck, you can ask. So yeah, you have already read all these things, so I'll just give a brief overview on this. So yeah, Coriolis, this works on the Coriolis, it uses the Coriolis force, I should say. So using the Coriolis force, it will basically, whenever a phenomena is happening that we are trying to quantify, based on that phenomena, what changes that we have to figure out, and then we have to figure out how can we use that change to measure some electrical signal, maybe how can we convert that change, effect of that change, into an electrical signal. So this is the idea of all the sensors always. So in this case we are converting using this Coriolis force, and we are basically suspending a mass. Again it is the same way, it is done in the same way in most of the MEMS sensors. So there will be again a proof mass will be there, and that mass will be used to that will be placed in a frame. So that frame basically helps you understand like with how much force or how much Coriolis force you are facing. So this proof mass will be placed in the middle of the whole structure. So based on the whichever axis, so now since it's suspended in a 3D environment, so basically it can measure how much Coriolis force is applied on in perpendicular to which axis. So basically Coriolis force is a nice property. If you are rotating along this axis, and you are rotating along this side. So basically, if you notice, you are rotating perpendicularly with your axis, right? I will go to this figure, this will help. So this, if this is your axis and if you are rotating this side, so basically you are rotating perpendicular to your z axis. Now Coriolis force will always be perpendicular to both of these, so it will be in the y direction. If you are moving in the y direction, maybe it will be in the x direction, so it will be perpendicular to both. So from that you can understand corresponding to which axis you are facing this force, if you can measure that very well. So since we have a suspended proof mass, and we can measure how much it is facing, how much force it is facing, and based on that we can understand that how much Coriolis force is applied at which direction, and based on that we can understand that at which axis, along which axis there is a angular velocity. So which will be the axis that I will be choosing? So basically, if I face a Coriolis force at this angle, basically I will understand this is the axis that I am getting. I am getting the, I mean, sensing the force against, because this is at the perpendicular to this Coriolis force direction, and I know I am rotating in this direction from the direction of the Coriolis force. So yeah, so by measuring this, I can easily get along every axis what is the acceleration, and by measuring linear acceleration along each of these three axes and angular acceleration along each of these three axes, basically I can find out, I can sense 6 data. If you notice, I can sense 6 data. So basically these has names. If we are sensing angular velocity or angular, this does not only help us understand what is the angular velocity along each of the directions. If you notice, it will help us understand the pose of the system as well. So what is the roll, pitch and yaw? These are the three terms very frequently used in robotics domain, or in when I am trying to sense the position of a vehicle maybe, or the positions of a drone. These three things are very frequently used. So roll, pitch and yaw are three things. Like yaw is the rotational angle, with how much angle I am moving along the z direction, not along the z direction, with respect to z direction. That is basically my yaw. So when you are traveling using a car, consider this is a car, this is the roof of your car. So along the z direction, if you are moving, how much you are moving, keeping the z direction, considering the z direction as the axis, that angle is called yaw angle. So if you are measuring that angle with respect to x axis, basically you are measuring how much pitch you are having, and if you are measuring that using y axis, maybe you are measuring how much roll you are facing. So basically, if you are considering a vehicle, a ground vehicle, for ground vehicle obviously pitch will be there if there is a slanting road, maybe in that slanting road the car is trying to go upwards or downwards, then there will be a pitch. Otherwise there will be mostly yaw, and there will be a roll if there is a slanting road again from side to side. Yeah, so usually yaw is
So,
something
sir,
that we
can
measure
we
in
say
case
that
of,
IMU, sir,
sorry,
excuse
yes,
me,
yes.
can we say IMU is for the linear acceleration and gyroscope sensor is for angular acceleration? Can we say like
No,
this?
no,
No.
no. Basically, IMU sensor consists of multiple sensors. So, inertial measurement unit is something, a sensor unit that uses the inertia of a proof mass or a seismic mass. That is what I told at the start. Do you remember? So, it is using that inertial property of a mass. Using that, what are the things that we can measure? First thing that we can measure is the linear acceleration using accelerometers. Second thing what we can measure is the angular accelerations or angular velocities using what? Gyroscope sensors. Now we'll come to magnetometer, we'll come to that. So combining all these things, basically from IMU unit, we get a 9-axis. When we say a 9-axis IMU sensor, so basically I just told you about 6 measurements. 3 along your linear axis, 3 along 3 across your, like if you are considering those axes as your rotational axis, then what are the angles or what are the accelerations around those axes. Those are other 3 measurements. So this gives you 6 DOF, and if you measure the velocities along with the accelerations as well, that gives you 3 more measurements. So basically these are 9 axis IMU sensor measurements, and it helps you understand the orientation of the object, it helps you understand the velocity of the object, it helps you understand the gravitational forces that will come to. Those are measured using the magnetometer. So do you understand what do I mean when I say inertial measurement unit?
So that means if I say IMU consists of 3 sensors, 3 in acceleration, 3 is
Yes.
gyroscope, and 3 is magnetometer.
Yes, yes. So this whole pack works in the same principle, and that is why such a name. And this gives me all the data I need, most of the data I need to understand what is the pose of the vehicle, what is the linear and angular velocities of the vehicle. I'm telling a vehicle here. It can be any mobile CPS. It might not be any vehicle. It can be your phone as well. In our phone also these sensors are present. Yeah. So yeah, that is what. So if we come to magnetometer now. So gyroscope sensor again works in the same way. The way we told that accelerometer sensor works. So here also you can use multiple different materials. In this case, if you are using a gyroscope sensor and you are trying to measure, basically you are trying to measure the inertia along in perpendicular to the x-axis or y-axis or z-axis by measuring, due to the Coriolis force, how much force is applied on the material, and measuring that. How do we measure that? We measure that by changing the electrical property. Again, in this case, again we are using capacitance again between two materials. If we measure how much with how much capacitance we can measure between these two electrodes, then we can understand with how much force that mass is moved. And with the force, with how much force the mass is moved, if we can quantify that, we are basically calibrating that with how much angular velocity the object is moving. So all these sensors will be needed to be calibrated before you use, because you don't know what is the capacitance value. The manufacturer will know, obviously. This is how the manufacturer calibrates the sensor. Basically you will know when it is at the resting phase what is the capacitance. Then it will know if I am rotating it along z axis with this much torque. Obviously we are measuring with how much force we are moving it using torque. uh, uh, we use forces when you are measuring linear things. We use torque when you are measuring the angular stuff. So yeah, obviously it will calibrate the sensor. If we are rotating with certain amount of torque, then what is the amount of the capacitance value that is changing. By measuring that, we can easily understand what is the current velocity and what is the acceleration. Yeah. And third thing is the magnetometer. So magnetometer, basically here the magnetometer, again this can be done in multiple different ways. Here we are using a Hall effect based sensor for as a magnetometer. So basically you know how, what is Hall effect, by the way? Anyone?
So in the Hall effect, if the moment there is the charge
Hmm.
which is accumulated, and with that the voltage across is changed. So whenever there is some magnet, so
Yes.
at the other end some charge develops, the moving charge, which shows that there is what you say, uh, mm,
Yes, yes, you are right.
some
You are right. You
some
are right. You are
magnet
right.
is
The idea
coming.
is correct. So again, it's simple. If we have a metal sheet, obviously certain materials supported. If we have a metal sheet, and if you are applying some certain, uh, it can be, it can go both ways basically. If you apply current in a magnetic field that is perpendicular to the current. So basically the idea is when the magnetic field is perpendicular to the current flow, basically we observe Hall effect. So these are found in certain materials. You will not see this in all the materials. Obviously, there are certain specifications that are followed. Then only these are found. So using those materials, we make Hall effect sensors. So in these sensors, what happens is, based on the amount of the change in the current or the magnetic field, we can measure what is the change. The change in the magnetic field will obviously cause the change in the electricity that is passing through the material, and by measuring this we can
Sir,
understand.
previously one the Coriolis force, one numerical is there. So I want an expression of that Coriolis force. Fc is equal to 2 big sigma into m. That is the force. It is not in the slide, but one numerical is there to calculate the Coriolis force.
So you are saying Coriolis force, how to calculate the Coriolis force, right?
No, no. First of all, the expression what I saw in internet, it is 2 times big what you say omega into
Uh,
m. That is the expression. Is it correct? Because the
Again,
slide doesn't have any expression.
yeah. So it depends. It depends. You do not read from the internet if you do not understand what mean. So basically, it is simple. So this is a force, and the force will be equal with what? It will be exactly same as it's since it's in the opposite direction to the direction it is moving.
As expression of force we have to calculate. Na? Fc is
Yes,
equal
it
to,
will
if
be
we
same
see
as the expression of
mathematically,
force we are moving it with. That is what I mean to
so
say.
Fc is v cross w. If we say v cross w is the Fc.
Consider the velocity of the object that you are in the rotating frame. It is a rotating frame, so it's an axis. Consider in this axis, if you are rotating an object, the object is moving with v velocity. So with the v velocity, if it is moving, and maybe omega, consider omega is the angular velocity of Earth. Okay. So in that case, the big omega that you are saying, that is usually an expression that is used to express 2m omega. M mane the mass of the object, suspended object. So basically it is 2m omega into the velocity your object is moving with. This should be the force, amount of force that you if you want to measure the Coriolis force, this should be the amount of force. So basically a Coriolis force is a vector. Basically it is not a scalar value, so its direction will be opposite to this force. So we denote it with minus 2m into omega and multiplied with the velocity that we are that the object is moving with. Do you understand what I am trying to say?
Yes.
So what I'm meaning to say is, do you understand why it is happening like that? I mean, why is the Coriolis force then with that much amount? 2 into m into omega
From where
into the
this 2
velocity.
is coming? From where this expression 2 is coming?
If you draw a free body diagram, and if you draw what are the forces that you are getting that are coming that the object is facing, you will see, if you equate those forces, you will see how the 2 is coming. You try to do it yourself. If you don't understand, you ask me in the next class, because this is not something that we are basing the course on. This is something which we are using to build CPS. So we are not reading a physics course. Had it been a physics course, I would have explained it to you. But to understand this, again, so if you draw a free body diagram and if you draw all the forces, and then you will understand that why there is a 2 coefficient 2 is coming. Obviously not 2, actually minus 2 should be coming. So why the coefficient of minus 2 is coming in the Coriolis force expression. So it is coming from the fact that it is basically opposing certain amount of forces. So you try to figure it out, try to work it out. In internet there are multiple sources will be there. From some source you try to figure it out. If you don't understand something, you cite that, take that material in the next class and ask me what you don't understand from the material. Fine.
Okay.
Okay. So if I want to just clarify, if you get some questions in your assignment or in your exams regarding this, mostly there won't be any, should not be any. If you get any questions like this, the facts using which you will be, you will have to solve this, those will be given. Okay. Mostly the facts that you need to solve such a question will be given. If those are not given, you can definitely do an internet search. Otherwise, those will be very evident. Those, like, it will be like Newton's second law or third law, the evident law of forces. You can use that and you can deduce it if that is already not given. Okay, mostly if such questions are there, the logic or the fact based on which the logic is meant should be given. Okay, anyways, so yeah, again, as I was saying, gyroscope sensor is again measured with the capacitance. Yeah, Hall effect. So Hall effect sensor is basically it induces a basically whenever you are applying certain magnetic field, and a certain magnetic field, you are observing a certain amount of potential difference, and based on that you can measure that potential difference. If you can measure that potential difference, basically you can measure how much magnetic effect you are facing. From that magnetic effect, you can know what is the how much magnetic field is effective on you, and like that you can measure using magnetometer. That is what we measure using magnetometer actually, by measuring the what is the amount of current flow or the Hall voltage that we are facing across the material or the sheet that we are using. So basically we understand what is the magnetic field that we are facing, what is the amount of magnetic field that we are facing. Okay, so again, this is one way to do it. There are other ways to do it. So wheel speed sensor leverages this Hall effect. How can you leverage Hall effect in case of, if you understand, first thing, if you don't have a wheel speed sensor, you cannot actually guess. See, this is a very interesting thing. Now we have already discussed we can measure the linear accelerations along each of the axes. These are very practical problems. To solve these problems, people think of some way, and then only these kinds of sensors come out. So these are all basically revolutionary thoughts that came out, and that is why the autonomous vehicles are possible today. So as we told, we can measure the acceleration along each axis, right? From the acceleration, if we know, if we integrate, if we know where we are starting from and we integrate, we can easily we can measure what is the velocity. But that value is not always accurate. There will be noise. Okay, since it is working on certain phenomena, that is depending on how much that material suspended mass is moving. So we are basically translating the movement of the whole CPS or the whole mobile CPS that we are trying to measure the acceleration or the angular acceleration of. We are measuring what is the velocity it is facing, or what is the acceleration, with how much acceleration it is moving along the along certain linear axis or around certain axis. So we measure that using that suspended material, but that might not be very accurate. There may be precision issues. For that we need wheel speed sensors. Wheel speed sensors will help us understand, since we can measure how big our wheels are, if we can measure with what speed the wheels are moving, we can easily measure that how much path am I crossing while the wheels are rotating, maybe in a second. That will help me understand the actual velocity of the vehicle or any robot per se. So yeah, so this is the idea of precisely measuring what is the actual velocity. So what I am trying to say is, when you are trying to measure velocity, the MEMS based, IMU based sensors are not very helpful. Those are helpful in measuring how much change in velocity is there. So the acceleration is a very, trustworthy data that we can get from there, but to measure the velocity kind of thing, we have to use something like wheel speed sensor. We have to take the help of wheel speed sensor. So again, so we know in vehicles we are using electronic braking control modules like EBSM, that is mentioned here as EBSM. So again, there are different ways to brake in vehicle. We will come to that as well when we will be reading actuators. So in this case, when you are using some electronic braking system, so there you keep this wheel speed sensor, that is basically a material that shows that behaves under Hall effect, behaves differently under, has this property. So it is placed there, and basically it is placed with a permanent magnet, and since there is a very less amount of air gap between the sensor and the wheel, so based on the rotation of the wheel, the magnetic field changes, and based on the change of the magnetic field, we can measure what is the amount of electricity that is flown through the material, and that will help us understand if the wheel is moving, with how much velocity it is moving, and by doing that we can understand what is the velocity of the actual vehicle or the drone, whatever speed of whatever CPS I am trying to measure it. So yeah, this is the idea, but again there are other ways to do it as well, but this is the most precise way to do it. This is what is mostly implemented in most of the vehicles. This is how it's mostly done. So yeah, any questions up to this? It's understandable, right? So yeah, moving on to the next part. Once I'm done sensing what is the state of the physical state of my system, what is the next thing to do? Basically we are skipping to the actuator. In between, what happens, what are the things that happen when once I sense the state of the system? Anyone? In cyber-physical systems, what is my next objective?
Then after getting the state, we want that state to be what you say communicated to actuators.
Mm, that is one way to say it, but that skips a big part. So what are we sensing the states for? We want to know.
To control the system.
That is a very vague comment. Yes, you are right, you are not wrong, but basically what you are trying to do is, when you are driving a car, if you are measuring with field speed sensor with how much speed you are moving, what are you measuring for? Measuring that for, so that obviously you can control it, but to understand if that matches your reference or desired speed. If not, then only you control your car. You control your car to drive the current system state that you are sensing using your sensors towards a certain reference or desired value by controlling it. And what helps you uh, impose those control signals on the physical system? There comes the actuators. Makes sense? So we are skipping this part in between. So sensors and actuators are closely implemented with respect to the plant, and the other part is basically can be remotely deployed from the plant, can be in a remote location in some cases, can be in the same module but further from the plant. But these things, sensors and actuators, should be implemented in such a way so that they can, especially sensors, since you have seen the sensors are basically working, trying to understand, measure the situation or the pose or the velocities of the actual system, so it should be attached to its body somewhere, it should be attached to it. So it is attached as nearly as possible to the plant. Again, actuators are also actuators will obviously have certain modules implemented in the plant so that you can supply the force or the amount of control signal command that you want to execute on the physical plant, so that the system state that you have sensed, that goes towards your desired value, and you can control the system as you want. So yeah, that is the idea. So with this, there are obviously different kinds of actuators. The actuator, and here we have given one example, that is hydraulic brake booster. we all know from childhood we are reading about these things. We all know how these things work. Obviously they are using some incompressible fluid like oil, but obviously there is a chance of getting leakage or something like that, because you need to have it leak proof, so that you are basically trying to apply some force through here, and based on the area of the piston you are using a piston to press the fluid inside this pipes. So based on how much pressure you apply, they will also move, and based on their movement these pistons will also move, and based on this as the pistons move, the wheels of the vehicles are pressurized and they are supposed to stop or decelerate. And this is how the brakes are usually applied using hydraulic brakes. And in anti-lock braking systems, this how much I mean, you know what and how anti-lock braking system works. Why do you use it? Anyone? If you have I mean driven a car, or if you have rode a bike, you will know. Obviously you have seen. If you even if you don't know, doesn't matter,
So
you have
whenever
seen
there is
there is
some,
a feature, ABS
what do you
feature
say?
available, right? Yes, yes, please go ahead.
So whenever there is some sudden force or impact,
Hmm.
so this ABS system energizes, and then it will give actuation to some inflation system which will save the driver or passenger.
Again, this is very superficial definition. We all know, like it does something good to us. You are defining it like this, but you are right. You are right. That is the objective. But I am talking about the specifics here. So specifics is nothing special. Basically, if you apply brakes for very long, maybe there is an icy road. In an icy road, if you apply the brakes for very long, then your car may skid. So instead of applying, maybe there are too much dust in your road, there are too many pebbles in your road. If you are applying brakes, the pebbles will roll and your car will skid. To stop it from skidding, we don't apply brakes continuously. We apply brakes in a discrete way. That is how anti-lock braking system works. What you are saying, that is basically regenerative braking. That is also nowadays used in most of the vehicles. So yeah, read about this. These are very interesting. We will not go much into this because that is not the objective here. About this, you will get the details of these things anywhere in internet. But we will learn more kind of how to model a system, how to model the communication module accordingly. All these things we learn in this course. So these are something that work on the basic physical properties, and you can learn this by searching in internet. And yeah, so hydraulic is used hydraulic is an actuator that is used for this purpose. So again, this is an actuator that is this is basically using what, this is basically a mechanically activated actuator, right? Now there are obviously other actuators as well. So hydraulic actuators are mechanically activated by applying here, and it works on the pressure. Based on the pressure, based on the volume and pressure, we know the P1 into V1 equals to P2 into V2. If the volume changes, the pressure will change in a opposite inverse proportionally, the pressure will change. We use that property, and using that property we actually apply the brakes in each of the wheels. So there are obviously other actuators as well. So in this case we use hydraulics are very popular. You will see in industrial CPSs or in automotive CPSs. The reason is it force that we exert using hydraulics are very high. Okay, so that is why we use this. Obviously it has to be leak proof. There are many things. We can do the same using air as well. Air is also a medium that we can pressurize, and but obviously it cannot be only air. It should be something like, so that the air has no it should not be at all having any vapor. It should be controlled. In a controlled way you can use air to apply brakes or use as actuator as well. So those are called pneumatic actuators. We will not go into that, but the problem will be, what I was trying to say was, the force will not be this high. Considering the material that you are using, the forces, amount of forces change. But this is kind of,
Air actuator, sir, what you want to say that air actuator force is less than the hydraulic one, na?
yes, yes. That is what I'm trying to say. I was trying to say that this is one way to make actuators. There are other ways to make actuators. One way is this, using hydraulics. These are very popular because they can handle very high amount of forces. They can exert very high amount of force. The speed is not very high, very fast. It will take a little amount of time. There will be a little amount of delay between what you apply and what actually the system sees. But it can handle very high amount of force, but that cannot be done if we are using compressed air or something like that in place of the oil or these kinds of materials. So those are called pneumatic actuators. They are, obviously they will not be able to handle this high amount of force. Other actuators are also there, as we learned piezoelectric effect. There are materials with piezoelectric effects. Those are also used for actuation. Now we all know about electrical actuators, like we use directly by changing the electrical field, we can change the rotation of DC motor. We know these electric motors can be directly actuated. Whatever amount of rotation we intend, we can equivalently we can increase the voltage, and similarly the speed of the wheel will be increased when we are using BLDC motors in the electrical cars in modern days. But obviously it will not be exerting very high amount of force, so that cannot be, that is not a very ideal way. I mean, electrical actuators are not very ideal to be used in case of braking heavyweight vehicle or heavyweight machineries, but they can be used in moderate level, obviously. But they are obviously very fast and they are very precise. So depending on the situation, what are you expecting? If you are expecting to handle very heavy loads, you use the hydraulic ones. If you are expecting to be very precise and very fast, you can, but you can compromise on the weight or these kinds of thing, then you can use electrical or the piezoelectric effect wala jo bhi materials hai, we can use them. So yeah, so depending on the situation we can decide what to use. If we need very high precision, we can use the electrical ones. If we need high force, we can use the mechanical ones like hydraulic. Chemical ones, they are mechanical ones. Yeah, so this is something. Now let's come to analog to digital converters. Why do we need converters? Anyone? What do you
Because
think?
normally the forces are analog and
What do
control
you
is
mean forces
digital.
are analog?
So sensing, what we say, a sensor is mostly an analog sensor.
What do you mean
Physical
when you say analog? And what do you mean when you say digital?
physical phenomena are more or less analog. They are not digital. Now, once you have to convert that physical phenomena into what you say controllable digital circuit, so we will convert that physical phenomena into digital. So that is why analog to digital converter is required.
Okay, tell me what is a voltage? How is a voltage measured? Is it an analog signal or a digital signal?
Voltage is analog only.
So basically, analog meaning a continuous signal. Am I right?
Yes, yes, yes.
So this is what I wanted to hear from you. You are right. What you said again, you are correct. So basically, it is very hard for us to measure if we continuously measure something. Even here, when you are making a CPS, we are not continuously measuring the sensor data. We are having certain sampling period, right? So after a while, we sample the data instead of continuously measuring it, because that is not possible. When you are making a computer with that much frequency, if you use to do certain tasks, you have to compromise somewhere else, right? So we will have certain sampling period. After each sampling period, we will sample what is the current voltage. This is how we measure the voltage. So whenever I am trying to do something with the physical system, whenever I am trying to control the physical system, I cannot do it continuously. I have to do it in a discrete way. So these are the two terms that you should remember that will come again and again in this course: this continuous time frame and discrete time frame. So discrete time frame is what we do computation in, and continuous time frame is what physical phenomena are, and the physical phenomena occurs. When we need to convert between these two, for converter we use this ADC or DAC. So whenever there is a physical phenomena, when we need to measure that and do something, make sense out of it, we use analog to digital converter. Now what do they do? These are very straightforward ways to do it. So basically, what are we doing using ADC? Anyone, did you understand from the course?
We convert analog signal into what digital
How?
signal.
How?
Like
What is
say
the idea?
suppose 1 0 is digital minimum, what we can say to start with. 2 digit is the minimum digital signal, what we can say. So now say suppose if we want to increase the precision, then we will go to 3 digit, 4 digit, 5 digit, 10 digit, like that.
What do you mean
So
when you say increase precision?
say suppose if I have to say 0 volt and 5 volt, suppose.
Hmm.
So if I mark 0 volt as 1 digit and 5 volt, so ulta. So 0 is, say suppose 0 volt is 0 volt, so 0 digit and 5 volt is 1. So now if I have to uh, change that 0 to 5 into, say suppose 3 level, 0, 2.5 and 5, then I will use 3 digit, like that. So if I increase the more, what you say, more precision, then 0 to 5, I can step to 8 digit also, 10 digit also. Like that,
You
I
are
can
right.
have.
You are right with a simple flaw. So basically, again, these things are measured using a range, not using one value. So basically, I am telling when the voltage value is in this range, I denote this with 0, 0. Maybe V is in 1.51 to 2.5 range. I denote it with 0, 1. This is how you are saying, right?
Yes, yes.
So it is always a range, isn't it? And when you say precision, it means the range should be minimized as much as possible, isn't it?
Instead of 0 to 1.5, I may go to
Yes,
0.0 to 0.5. So that is,
correct.
I
So the
am
range should be
increasing.
minimized. Shorter the ranges are, better my precision is, right?
Yes, yes.
So this is the idea. Nothing, very simple. How do we measure continuous signals? Let's break it down into certain levels. How many levels? That depends how many bits we want to use. If we want to use, we have maybe 2 bits. Basically, how many binary numbers can be formed using 2 bits? Obviously 2 bytes actually. Now bits, if we use character, obviously we can say bits, but I'm not going to that. Anyways, what I mean to say is, if we have only 2 bytes to express the amount of signal or the signal, then basically instead of measuring the signal, if you want to remember this value, maybe 2.56786, it will take many bytes, right? It will be stored in certain, maybe I think in double. If you want to do it in C, some C embedded C, You may need to use a double will be using maybe 8 bytes or 4 bytes depending on the compiler, and that will take more space. But if you find out that I don't need that much space, instead what I can do is I can be happy with this much precision, then I can store this much. Even to store this much also you will need more space. So instead of doing this, let's do something. Let's break it down into certain ranges, and you know it will always vary within 0 to maybe 5. So you know within this, if you try to measure this, you need not measure it very precisely, but you know if it is between from 2.51 to 2.59 maybe, I have to do something. So instead of exactly measuring it, if I use only 2 bits to measure this whole thing and understand whether the signal is within 2.51 and 2.59, and I assign that with certain value, maybe 2.59 maybe I say, and I assign that with 10 or 2, then whenever I see 2, basically I understand that the voltage value is within this amount of volt. So by understanding this, basically when the measurement, the sensor measurement gives me this value, a value within this range, I send it as 2 in my control unit, and the control unit decodes it. It understands that it is basically the value is within this range actually, and accordingly it does the calculation. So this is how it is done. But to send the value we need analog to digital converter, because other than this we cannot actually measure. Now more precise we want to be, as you are telling, more precise we want to be, more bits we will be needing. In this case I was giving an example where we don't need to be that precise, maybe measuring from 2.51 to 59 is okay to the so we are precise till the 10 to the power minus 2 level, so that is enough for me. So for that you define 2.51 to 2.59 one level, maybe 2.6 to 2.69 another level, like that you can keep on defining. So you can define it being even more precise, depends on how much memory you have. So yeah, not going into this further. So this is the idea, I guess you all understand. So this is how signals are converted from analog to digital. Now there is a structured way to do it. What do you mean by MSB?
Most significant bit.
Yes. When we are doing it from the measuring it from the left, the most significant bit becomes the left one, right? Which one is the most significant bit in this case? Anyone?
In this case, 1011 is the most significant bit.
Yes. So others, you are understanding, right? MSB and LSB, this concept should be with you already, but still I am asking just to be sure that you are in the same page. You are all are in the same page. Kunal, Sandeep. Okay. So yeah, so it is the opposite of what I was saying actually. So the most significant bit here will be the where what is the most precise measurement to me, that is the most significant. So the idea of DAC is the exact opposite to this. Why do we need DAC? Again, we need to convert the digital signal to the analog signal when we are actuating, right? Actuators will not understand the digital signal, because yeah, they will understand the digital signal, but eventually when they actuate on the physical plant, The physical domain does not understand the digital signal. So they will have to convert it from digital to analog, and obviously that is how the actuators understand what the controller is talking to them, and it converts the signal. How does it do that? You understood this math, right? Anyone who did not understand this math has any problem with this math? This is very simple math using Kirchhoff's law. If you get the voltage along the loop, you will understand what is happening here. Based on the bits, change in the bits, you apply resistance to this circuit, and based on that you can measure the output of the circuit, that is the analog output of the circuit. Anyone who did not understand, I think professor elaborately explained this, so I don't need to explain this. You can expect something similar in the questions as well, maybe in exam. So understand this very well. If you don't understand this, you can tell me now. So I am considering that you understand this very well. So you are not going into this. Similar problem can be given for ADC as well. If possible, you try to find out and read about this from this book. Okay. So these concepts are taken from this book only. I mean the slides are made from this book, this part of the slides. Yeah. So now we come to the CPS Compute Platform. So we are done with reading how we sense the physical states. All states cannot be sensed. Understand that very well. So you cannot sense everything which is considered a state of the system. So there are certain measurable states for which we can make sensors. There are certain states that we cannot make sensors for. So after we sense it, we send it to the control unit. How do we send it? We send it via a certain medium. We'll come to the medium. But before that, once I compute the control signal, I send it back and the actuators actuate it. And in this process, I need to translate the analog signal to digital one so that the controller understands it, and translate the digital signal to analog one so that the actuator can actuate to the plant. So these things we have covered till now, we have discussed till now. So CPS Compute Platform is basically an onboard computation board that is there to compute whatever sensor data you are getting, and based on the sensor data you are basically computing what should be your control command. Now in vehicles there are different boards, microcontroller boards used for this. They have very constrained amount of memory and very constrained amount of computation bandwidth, and very constrained communication protocols supported by them as well. But eventually the automotive industry is trying to shift to high power computation units, and they are trying to implement a centralized kind of communication unit, which will be considering doing all kinds of computations altogether. So basically if you see in any distributed CPS, now CPS is like a vehicle, maybe there are multiple sensors. So in multiple sensors are placed in multiple places. So multiple sensors in multiple places, they should be sending data to different control units. I will not draw here. Anyways, so what I mean to say is there are different control units for the reason we need to handle different things. So different control units handle different things, and they are in the vicinity of those particular sensors which will be sending it data. Mostly, it might not be the case always. depending on the situation. There are many things they try to optimize when a manufacturer is manufacturing a CPS. One of the things is, while the signal that you are carrying from the sensor, that should not get dissipated. It should not be very long. The conductor should not be very long. Then the value measured will not be very precise. So there are many certain things. So depending on that, the decision was to build a distributed CPS where there are multiple control computation unit. So nowadays all the vehicles are having that, and they are connected with certain communication protocols, right? So from sensor you get the data, you sample the data basically using the sensors. Obviously whatever you do in the computation, for computation we cannot do continuously. In real world everything happened continuously in the physical system, in the physical world, but in digital world we do it discretely. In discrete time frame, the sensor senses the data, sends it to the ADC, the ADC communicates it to the processor. The processor actually computes certain data and again uses the DAC to convert it to convert the digital signal to analog signal, and the actuator actuates it. Now these processors, if there are multiple processors, there is a communication between them. So there are communications between sensor and processors. There are communications between processors and actuators. There are communications between multiple processors, because they may need to communicate and understand, make sense of certain data, right? So there are different communication channels if you see in a CPS. So different communication channels use different communication mediums. All the communication mediums, like we talked about the different kinds of sensors, different kinds of actuators. Obviously we are reading certain examples out of them here in this slide. Now but there are multiple possibilities, multiple such possibilities. That is why I wanted to convey by going through these slides. So there are multiple communication mediums or communication channels or communication protocols as well. In this case, the example, as an example, we study the control area network, that is heavily used in automotives. In automotives, basically, since as I told you, there are multiple control units, those are basically, these control signals are basically carried using CAN. So there are different control units to different things. So different CAN buses are present to carry different control signals to different place. So what I mean to say is, these are all very well segregated. Okay, you can see that, you can find that out from this picture. So in this picture, if you see, I'll zoom it even more because the text seems to be very small. So if you see all these blue ones in a vehicle, there are multiple objectives of multiple controllers, all of them working together, then only the whole vehicle is rolling.
Sir,
Or
I think slides are not moving. Excuse me, sir. Slides are not moving.
okay, I'll stop presenting and present again. Is it visible now?
Sir, yes, sir. But previously, what you have was static.
Okay, sorry. You should have told me earlier. So I was stating, basically we have talked about these sensors, different kinds of sensors that we are doing and that we use in CPS, different kinds of actuators that we use in CPS, and these sensors and actuators at the plant end, the physical systems end, and they send data to ADC. ADC converts the continuous signal to a digital one, and so that the processor can process, and the processor sends data to DAC, so that the digital signal becomes a continuous one, and the actuator again actuates them on the plant. So to communicate between, so what I am trying to say is, the sensors are placed in different places. They cannot be placed further from the plant because they are trying to sense the actual states of the plants. So the data needs to be carried to the processor, but that should not be very I mean that should not be the for conduction, for to conduct this signal, we should not use very long path so that the signal gets dissipated and we get an imprecise value. So to take care of these, usually most of the CPSs use distributed control units, okay, to obviously execute distributed control objectives, okay. Automotives are one of them. Mostly in these CPS lectures, you will see most of the examples will be around automotive fields. Obviously, there are other CPSs. They have similar properties, but in a very different scenario or to, I mean, or for certain different objectives. But here we will mostly talk about automotives. So, since we are talking about automotives, we take the example of CAN, control area network. So, as I was saying, from sensor to processor, there is a communication medium needed. From processor to actuator, again another communication medium needed, because again actuator has to be at the vicinity of the plant, but the processor might not be, because it might not be safe for the processor to be near the plant, since there can be some accident and the processor may get broken down or something like that, may be damaged. So usually those are kept safely enough, but the signals should be strong enough or precise enough, that is going from the processor or coming from the sensor. So for that we need to use certain communication protocols that do not impose much delay and that gives me precise values. So the main two criteria while choosing such communication protocols or deciding how should we communicate this data is they should be very fast, they should be very frequent. Since we are trying to convert a continuous signal to a discrete time one, we have to sample really fast, like in millisecond range or maybe 0.1 millisecond range, okay. So if we sample that fast, then the data also has to be communicated that fast. For that, the communication medium or the communication protocol has to support that fast data communication without very high implementation, very heavy implementation, I mean. So what do I mean by heavy implementation? Depending on how much it is costing for me to implement the communication channel, that will decide how much the CPS will cost. If it's a consumer CPS, I mean consumer centric CPS that is designed to sell to the consumer, like power grid is a CPS that is not prepared to sell. Basically we are selling the power that we are generating, distributing the power we are generating. Basically we are using CPS to distribute, generate and distribute powers. But if we consider about automotives, there the whole CPS system is consumable. So since we are buying it, obviously the cost will increase. Yeah, obviously if the implementation cost increases for the power grids as well, the electricity charge will increase. So to keep things within range, to constrain everything, we also have to take care of the cost. So usually you will see most of the communication protocols or most of the sensing, the way we sense or the way we actuate, those will be relying on very straightforward physical properties of systems. We have seen for sensors and actuators how do we do that. That is why MEMS is used. MEMS is very not that costly actually. So in this case we will learn how CAN is a communication protocol, that is how that works. So basically there are different CAN buses. Do you know what are the network structures? Different network structures are there. Bus networks, topologies, basically network topologies are there, different. So bus topology is there, star topology is there, mesh topology is there. So do you know about them?
Yes, yes.
So yes, so CAN networks use bus topology. So there are not one bus in a CPS. There can be multiple buses, but they are purposed to carry different signals. What do I mean when I say different signals? So that is where I stopped and again reshared the screen. So basically what I was meaning to say is there are multiple control objectives which are fulfilled in an automotive, and then only a vehicle rolls. Even when it is not rolling, then also there are certain systems that are activated, then only the car is able to stop and perform whatever it is supposed to perform. So for that there are different CAN buses that carry different signals for different purposes. If you see the blue blocks here, the blue blocks are mostly handling the things that is attached to the car body or the car chassis, if you see. Okay, now there are many automations that are done in this trunk, lights, in the central body module maybe. So those things are handled by one CAN bus. That need not be very high speed, so we provide a low speed CAN bus for these. Now there are other protocols, as I was saying. MOST is another one protocol that takes care of the media centric communications. What do I mean when I say media centric communications? Maybe the car is using a radio signal, maybe you are listening to a speaker while you are riding, maybe some navigation signals are also there. So when you are connecting to the internet or you are using the multimedia, when you are consuming the multimedia, that is handled by this MOST communication protocol. Okay, I forgot the full term for MOST. I guess it's multimedia related something. I forgot. So another, now what we will be talking about is CAN, control area network. But the most significant one where we use CAN is for powertrain. Powertrain meaning when you are driving a car, what is responsible for the power transmission of the car. So basically when you are driving the car, we are accelerating the car, and when we are accelerating the car, that amount of how much amount of force needs to be distributed to each of the wheels and how are they distributed, all these things are controlled. This data, how much force should we send, these data are communicated using CAN bus only. So basically, as we have seen how hydraulic brakes work, there are different ways these gears and the gearbox and the other actuators work as well. So I am not going into that, but what is important is how the signals are carried without any heavyweight implementation or without any time delay very frequently. So if you are delaying in sending these signals, there can be a fatal accident or something. So to avoid that, we use a very lightweight protocol that is called CAN, that was first invented by Robert Bosch. So nowadays also it is being used, but there are certain changes that are being made, and why those changes are being made, we'll come to that. As we understand the protocol, we'll eventually understand what is happening and why is that happening. So basically this works in a follows a bus topology, as I was saying. So bus topology means there are different CAN buses where multiple CAN outputs, like CAN consider there is an engine, there is a control unit that controls and that computes the data that it has to actuate to the engine, how much force the engine should generate. So to send that data, it is using a CAN data channel. So that CAN data channel is connected to this bus. This is a very high speed CAN bus which takes data from the transmission, the engine or the active suspension, from all of them, and ultimately communicates to certain diagnostic gateway or certain control units, or from control units to those particular engine control units where we will be eventually actuating those values, computed values on the physical systems. So yeah, so CAN is used for that. So why CAN? What is good in the design? Why is it so popular? So CAN basically works on very simple electrical property. It is basically two twisted pair of wires. First thing that is very good in case of if we when we use twisted pair of wires is it is resistant to attacks which are done using magnetic fields, because when we are using twisted pair of wires, no, so they have their own magnetic fields due to their twisted pairs, and that resists any magnetic field that are coming from outside. And this is a very good way to use a very good way to stop the interference to interfere from the signals that we are carrying, and using a twisted pair of wires to carry these precise signals helps us doing that. So we cannot we have to be very sure the signals that we are carrying to achieve this are very precise. So it has to be very lightweight, and it should not be costing very much, because since we have to be very precise, it has to use more and more number of bits, as we have discussed earlier in ADC to DAC, while understanding ADC to DAC. So it needs to use more and more number of bits to send a precise signal, but there has to be a way to not use that many bits for the signals that we should not be leaving any empty bits. That is what I mean to say. So basically what is done is, it is basically a network of modules, basically two wires, twisted pair of wires. Basically we measure the voltage between these two wires, and we understand what is the level of the bit that we are transmitting. So two lines are called can high and can low. In the recessive state, recessive is the state when these two are having no voltage difference at all. That means basically it is a 0 bit. And when in dominant state, in dominant state, I guess it is 0 bit, and the recessive state it's 1. So why dominant and recessive are named like this? Why we are naming it in an opposite way? Basically, when we are using a twisted pair of wires, basically this works as a AND gate. Why am I saying that? Because if both of them are carrying certain voltage, or if both of them are behaving in the same way, then only you are getting a high. If either of them are not behaving in a expected way, you are getting a low signal. So what do I mean by telling that? So dominant bit means that when the bus, basically can high takes 1 voltage higher to the 3.5 volt, and can low takes 1 volt lower to the 1.5 volt, basically there is a 2 volt voltage difference, then we call it a dominant bit. And when there are both are basically having no voltage difference, then we call it basically a recessive bit. And why dominant bit is encoded with 0 and recessive bit is encoded with 1? Basically when we are having a 0, then both of the wires should agree to that, and both of the wires has to go 1 volt higher from 3.5, and another wire has to go 1 volt lower than 1.5. Then only you get that difference. So it is basically an AND phenomena.
My both one question.
Yes,
sir, this CAN bus is what you say, duplex bus or half duplex, or say transmission reception is okay continuous, or one has to then continuous, okay, after transmission then stop, then reception will start like that?
Sequential, not duplex. It is sequential. When you are transmitting in one way, you have to finish the transmission, then only transmit in the other way. So
and then will receive.
Sorry,
that is half. What we say, we say half duplex, one way transmission.
Yes, yes, that is it is basically half. What I mean to say, it is a sequential. The process is sequential. That is why it is not duplex. It is half duplex, but to transmit and receive, we use two different channels. Make sense?
Yes.
So you are transmitting via one channel, you are receiving via another one. Okay.
So if the channel, so then we can straightforward have one transmission continuous and one reception continuous.
Yes, you can actually. Actually, you can, but usually it is repeatedly synchronized. Okay, for synchronization that is not done always. Otherwise, we will lose synchronization. So that is why it is not done continuously. But yeah, if you use For transmission you can use one channel, and for reception you can use another channel, another pair of CAN buses, but using one pair of wires you can do both. But usually for transmission and reception we use two different ports, but we can use the same bus. That makes sense what I am trying to say?
Yes.
Okay. So yeah, this follows non-return to zero encoding. I am guessing you all know what is non-return to zero encoding. Anyone?
Basically, the signal is always above what you say zero level. It is not bipolar; it is a unipolar. What I understood.
Yes, you are right again. So basically, in non-return to zero, you don't have a separate level when there is no transmission. So you continue transmitting whatever you were transmitting last. So you don't return to zero when you stop transmitting. So in this case, there are different ways of in non-return to zero. In this case I guess CAN bus uses, so when I say different ways to use non-return to zero encoding, I mean you can either count a 1 when the signal is changing, when it's toggling you can count 1, or you can count 1 when it's going to a high level and 0 when it's going to a low level or something like that. You can encode it like that as well. So we have already told how we encode CAN bits. Dominant state is encoded with logic 0. Dominant state is this, this, and recessive state is encoded with logic 1. This is a recessive state.
Significance is not understood. Normally, dominant state should be one
Yes,
logic.
yes, yes. That is what I was trying to say. How is it reaching dominant state? It is reaching
When
dominant state when both of the wires are agreeing to something, isn't it?
both the differences you said more than 3.5.
Yes, no. Basically, difference should be 5. So basically, the high CAN high should go to 5 volt. The CAN low should become around 0.5 to 0 volt. So both of them should change their voltage levels in order to get a dominant bit. That makes sense? That is understood?
So repeat again, sir, please.
What I am trying to say is there are two wires, two signal lines, CAN high and CAN low. So CAN high has to go 1 voltage higher to 3.5, maybe it will go to 4.5, and CAN low has to go 1 voltage lower to 1.5, maybe it will go to 0.5, right? So then only you get the dominant bit. And what does this signify? This signifies when both of them agrees, when both of them agree to a certain phenomena, then only this dominant bit will come, right? The voltage difference will increase when both of them change their levels. That is understood?
Yes.
Usually both of them are biased to 2.5. If they are staying there, then they are creating no voltage difference. That is what we call a recessive state. That also makes sense.
Yes.
Now, why your question is valid and correct. Why recessive state is marked with 1? Usually it is the opposite in most of the signals. This is because this is designed to act like an AND gate. In AND gate, 0 is a dominant bit, right? Do you understand, right? Why in AND gate 0 is a dominant bit?
If AND gate, zero is dominant bit. Yes.
Right? So this is why we call the signal 0 as dominant bit, the logic signal 0 as dominant state in this case, and 1 as recessive state. Now why is that? Because if you see, if there are multiple modules, consider there are multiple modules. Consider engine is one module, transmission is another module, both are connected to CAN bus. Now both are trying to send their signals. So what will they do? If they are trying to send a 1, they will increase the voltage, they will decrease the voltage difference between these two. That means they will stay in the recessive state. Correct? You understand what I am trying to say?
Yes.
Maybe at the same time, since it's a bus architecture, transmission is trying to send a 0 bit. What will happen? What will go through the bus?
Transmission only.
I am
Transmission.
transmission. So you see, this is an AND phenomena. So two signals are ANDed. When you are following a bus architecture, basically two signals are ANDed and then they are transmitting, right? Makes sense what I am trying to say?
Yes.
So due to this nature, usually dominant state is marked with 0 and recessive state is marked with 1. Okay? And when there is a continuous 1, after 6 continuous 1, there are different errors that we get. I'll are those taught in this lecture? I don't remember actually. Let me see.
No, that error is not taught.
Okay,
This is taught.
that will be there. I think in the next slides, I think it will be there, as much I remember. Anyways, what I mean to say is, in order to synchronize, there are 0 or dominant bits in between this continuous 1. But what I am trying to say is, this works like an AND gate. This twisted pair of wires, when they are used in a bus architecture, they are behaving like an AND gate. That is why dominant state is marked with 0 and recessive state is marked with 1. This is the encoding that we use while we are using CAN network. Make sense? This is the ideology. The idea made sense, right? Hello?
Yes, yes.
Fine. So yeah, non-return to 0, as I told, is used with bit stuffing. Yeah, what I was saying, after transmitting 5 consecutive bits at either dominant or recessive, transmit 1 bit of the opposite parity. This is what helps you to understand if it is performing in a synchronous way or not. Okay, since in not NRZ you are not self clocking, you can lose the synchronization. Since you are not changing the level when signal transmission is over, you don't understand if you are live or not. So to understand that, you keep on changing the levels when there are no data. After transmitting every 5 consecutive bits, you toggle. Okay. So yeah. So when you are toggling, basically this is what it says. If there is a signal that you are transmitting, you easily understand it. If there is a toggle after 5 bits, you will easily understand that it was the same data actually. And if there is a toggle, obviously there will be a toggle and the bit will stay there. Since it is a non-return to Z 0, the bit will stay there for longer. So you will understand if there is which data was there. So it won't be an issue. So this is how a CAN frame looks like. These are the divisions in a CAN message. So these are already written, so I am not going into this. Like we design any protocol, this protocol is designed like this, and the CAN transmitters, they understand the data, read the data from this data field. In the DLC field, this basically carries how long your data field will be, and in this data field there are 8 bytes of space which you can occupy and send data. This ID is everything that we need in order to gain the access to the bus. Like I was saying, transmission and engine both are trying to send together, and which one will be able to send? The one that is sending a 0 signal will be the dominant one in this case, and this dominance is measured by their IDs. So lower the IDs, higher the priorities in the CAN messages. Lower the IDs, there are more number of zeros, So basically they get more priorities than the others, even though multiple units start transmitting together. The one transmitting with higher priority or higher ID lower ID value will be transmitted first, and after the ID field is gone, it is usually for 11 bits. There are extended IDs possible. I am not going into that. So for extended ID, I think there is a marker also. Yeah, yeah.
My one question, very common question, very simple question.
Yes,
Like suppose we have two, you said ki transmission and engine. Okay, they are the two. What you say? Want to use communication bus.
yes,
Uh, there may be a situation wherein the transmission as well as engine, both data is required for this control system.
yes,
So if we are giving say like transmission as a less bit priority than engine,
yes.
so then how that will resolve when the both
Data are
uh,
required. I understand your question. So yeah, you have to design the system like that. So the signal that is most important, the signal that is given the least ID value, that should be the most important signal. Usually that is that signal, such kind of signals have the highest frequency. Now consider engine or transmission, depends on how many control units are using which data for I mean how many more control units are using the data. Depending on that, we understand the priority or criticality of a signal. So this is basically decided by the designer. The designer decides which is the most prioritized signal in this case. Maybe it chooses the priority of a signal depending on how many control units use it. Maybe it chooses the priority of a signal depending on how frequently it is used by any of the control units. Maybe it is decided by some other factor depending on the situation of the say CPS system. Now what you are saying, if both data are needed, now both are supposed to be transmitted, but only one will get transmitted. So what we will do is we will change their periodicities. Periodicities mane their sampling periods will be changed. If transmission data is sampled once every 10 milliseconds, engine data maybe gets sampled once every 11 milliseconds, then both of them will be transmitting together only at 110 milliseconds only, right? Do I make sense?
sir, how you have calculated
By
multiplying by 10 and
LCM,
11?
LCM.
As you understood.
Okay. So by choosing when what I am trying to say is this is not the only design criteria. Choosing the ID based on the importance, that is not the only design criteria. There are other design criteria in the system design as well. One of them is the periodicity of the signal or the sampling rate of the signal. By changing that, we can avoid this situation, the situation you just told. So now it will be seeing less such situation where both should be transmitted, but only one will be transmitted and one will be delayed. Obviously, the one that is preferred, that is having a lower ID, that will be transmitted first. The other one will wait after the other one transmits. Then only the control operation that needed both of the data, that will be done. Make sense?
Yes.
It will make more sense if, will it make more sense if I say the control logic is designed to know this, that it can be late for a while, so it needs to compute the system states or sample the system states or get updated system states by the time the new data comes, and then compute the control command. Does that make more sense?
Yes. Yes.
So what I am trying to say, it is not that straightforward. We are only looking at the can, how can works, how are we deciding what signal should be having what value and all these things, but the system design, it knows this is not that straightforward. There are other design factors. So by this design space exploration, a designer decides what should have what value and they have to find out if everything works well after the design. Then only the system is deployed and used in real world. How do we do all these things? That is what you are going to learn in this course. What you are learning now, these are just the components. These are just the components that we use. But how does a designer do all these things? That is the main crux of the course. You will see there are multiple things. How the system is designed, control system is designed, how the communication schedule is designed, how the communication schedules and the system designs are verified. Verified means there are certain criteria they have always have to be following, or how their performance are measured, how the cost is minimized. All these things will be discussed in the course. Make sense?
Yes.
Okay. So I am hoping you already understand what I was trying to say. Yeah. So when the bus is in recessive state, no, then we call the bus is idle. Okay, in CAN. So you have to sync after every 5 signals, same signals, you have to sync by changing the by toggling the signal. Yeah, this is another important thing. When the bus is idle, you are not basically doing that bit flip. You are flipping the bit when there are messages to synchronize and understand if you are transmitting them properly. Make sense? So then only you need to know. So the CAN is designed in such a way it does not do anything extra. Whenever what is needed, it is very minimalistic, and it is very fast because obviously it relies on the change in the voltage only. So yeah, and it only needs a twisted pair of wires and pretty well insulated pair of wires. That's it. That's the only requirement, and you have to terminate that with the 120 ohm voltage resistance. That's it. Anyways, so yeah, there are more number of identifiers that you can use. 29 bits is the maximum number of identifiers that you can use. So data frame, how does it look? I have told you. There are 4 different kinds of CAN frames though. Data frame is the normal frame where all these fields will be there, and there will be 8 bytes of data. Not necessarily 8. How many bytes of data, that is mentioned in the DLC. Based on that, you decide how long your data size is. Uh, Remote frame is there when the transmitter is requesting data from a specific node that does not have any data. The frame ends before the data, and the data field is not there basically. So error frame is something that only has certain error bits. We will come to that. And there are overload frames that basically introduces some delay. When there is an overload, it flags that. There are things like that. So there are obviously other protocols, but in CAN, how arbitration works, I told that already in briefly while I was discussing about when someone has very a lower ID, basically their data is transmitted. That is basically called arbitration in the CAN bus. And for arbitration, we only use ID field. We don't use the data field for arbitration. Basically arbitration is something we use to decide which data should be transmitted, and the one having the lower ID wins the arbitration. That is how we express, and by winning the arbitration it is allowed to send the data. Make sense? So now that we know how CAN is working, how does it work? These are all pretty self-explanatory. So yeah, there is something called acknowledge signal. When a receiver basically receives, it has to acknowledge. Bit stuffing we have discussed. Now the error frames. So there are 3 error states actually in CAN. So these 3 error states are, one is error active, another is error passive, another is bus off. So I am guessing that all of you have already gone through the lectures, but I am still, this is very important actually. So because this is where there are certain vulnerabilities in CAN bus, and that is why they are updating CAN protocol. So there are many vulnerabilities in CAN, not only this, there are many drawbacks in CAN, I should say. So one of the drawback that you will find if you compare it with other protocols, maybe with Ethernet protocol. In Ethernet protocol, we have different we can understand different entities by seeing their IP addresses, right? But in CAN, you don't get to see from which entity I am getting the data, because it is very simplistic. Anyone can send any data. Obviously, for that we have to maintain a static mapping, like this ID is transmitted from this certain ECU, like engine will only transmit the ID 1, 2 and 3 ID, transmission module will only transmit the IDs 3, 4 and 5 or something like that. Static mapping will be there and you will match that, and accordingly you will have to find out from where it came. The designer decides it like that, and the receivers also verify it on their end. This is how it is done, but the signal is obviously not carrying that data. So that is a drawback of using CAN. Now coming back to what I was saying, so there are 3 error states. Why 3 error states? Basically in active error state, we are prioritizing the error transmission. When I say prioritizing the error transmission means, basically I am careful when I am seeing the errors. So I am sending the errors as dominant bits, and by sending the dominant bit, obviously I am disrupting other signals. You understand that, right? Since CAN works like an AND gate, so it is disrupting signals, other signals. When there is an error, some node is facing certain error. So there are 2 errors, transmission errors and reception errors, obviously. Now for both of them, there is only one error counter, there is only one flag or one register that keeps on increasing the error value, error counting value. So when you are basically getting an error free message, receiving an error free message, so error count, if it is higher than 0, it is decreasing by 1, and if you are transmitting wrongly, basically you are counting increasing the error counter by 8. Okay, so like this, when you are crossing 127, you are going to error passive mode. There you are not prioritizing the error anymore. Basically you are sending errors as recessive bits. So why these 2 modes are there? Error active modes actually flags you that there is some error, you need to figure it out now. So if you are able to figure it out during the error active mode, fine. Otherwise it keeps on increasing. So transmission error is, if the transmission error is causing this, then obviously it will increase by 8, the error counter will increase by 8, and you will get reach 127 or 128 after 16 transmission errors. And once you are crossing 16 transmission errors, you are deciding that it is bad for the traffic if I stop the traffic just to pass the error. So you let others pass and you send a passive error flag and you wait for what? To go to a bus off mode if the error is not reduced by then yet. So basically it starts from error active mode. In error active mode, you are sending dominant error bits to signify that there is certain error from this for this signal. You have to figure it out. If this is figured out, or if this is flagged, if someone takes care of this in the CPS, it can be in automotive, it signals you, it tells you there is something internally, something wrong is happening or something like that. The driver understands or the driver stops the car, restarts the car, restarts the system or something like that, take some measure, and or you take it for servicing or something like that. There can be many reasons for this to happen. So if you take care of that, then fine. If no, then it goes to an error passive mode where you don't prioritize the error messages anymore, and that is just a delay before you turn the node off. The transmission node which was causing the error, when you reach the bus off mode, you are basically turning off transmission from that node. So after 16 more transmissions, it goes to the bus of mode from error passive mode. So if by while staying in error passive mode, if within that time the error signal is error counter is reduced and comes back to error active mode, then fine, you are coming back to error active mode, and eventually since it is decreasing, you will again get back to the normal transmission. And if it is not decreasing, if it's still increasing, you turn that particular transmission node for a certain amount of time. The designer can decide for how long the system can be in the bus of mode, and then reset the mode and restart it again, and it starts again with error active mode, so that it will flag the error whenever there is a transmission error or deception error. What I told
Sir,
makes sense?
in transmission, you said whenever there is error, the TC is increased by 8.
Yes.
But in the reception, if the error is there, so it is the REC is increased by 1. Why it is so?
What do you mean why it is so? I mean, you have to understand, right, that there are two flags basically. Error counter flag combines TEC and REC. Now, TEC represents that when there is an error for transmission, REC presents when there is an error for reception. That is why.
No, but the count increase.
Okay, I understand your question. You are telling why that is increased by 8, but this is increased by 1.
Yes, yes.
Ah. So, if you see, it is again very ideological. If you see the way CAN works, the error that you are getting when you are getting an error for certain ID, it is most likely to get, there should be most likely there is some issue while you are transmitting it. So transmission error is counted higher. We increase the counter higher from the transmitter's end. Make sense? What I'm trying to say? But who is receiving the signal on, basically when you are receiving the signal, no, basically the transmitter basically sends a recessive bit in the acknowledge field. This, the receiver has to send a dominant bit and confirm that it has received the signal. Now the only reason the receiver will not acknowledge even after getting that ID is maybe there are some errors in between, and that error must be caused by the transmitter mostly. Now there can be another reason, that the receiver was not receiving the data, maybe it was damaged or maybe it was slow or something, it could not acknowledge in time. Then there will be some issue, then it will be penalized less than the transmitter, because mostly the issues are from transmitter's end. That is why transmission errors are usually penalized more than a reception error. This is the idea here. Make sense? I mean, this is how CAN is designed. It depends on the design of CAN. It is not, you will not understand it if you try to find out why, but this is the reason they penalize the transmitter more, so that transmitter mostly causes the problems. And in this scheme, there is more chance of the transmitter to cause problems.
Basically, in reception, acknowledgement bit is, I think, more dominant. So that is why
More dominant meaning, while you are receiving a signal, you have to acknowledge by
not
placing a dominant bit in that acknowledge slot. Once you receive the whole data, then you will get an acknowledge slot, right?
now reception. If reception is okay, then only it will acknowledge as a one. That is
Yes,
why.
yes, yes, yes. So it mostly depends on the transmission. If transmission is doing something wrong, then receptor has no issues to acknowledge. Make sense?
Yes, yes.
So mostly it is a transmitter's issue. That is why it is penalized more. Hmm? So yeah, that is the scheme. And bus of mode I have explained. valid can frame. EOF is what informs you when the frame is ended. So basically you understand this mathematics, right? How the bus load is computed here.
So can you solve this problem? Because this example.
Actually I prepared another example for you,
Okay, no problem. Solve one problem, then that is the last one. Yes,
yeah, yeah,
yes.
yeah. So we'll end with this one, I guess. Yeah, let's solve this one. I had another problem prepared, so let's solve this one. So consider a canvas with baud rate 125 kbps transmits the following messages. These three messages are being transmitted. Data bytes, data in bytes are 1, 5 and 8. These are the values we get in DLC, data length code, and these are the rates. When I say 100 transmissions per second, I mean this is the periodicity, right? You understand this, right? When I say this, these two are same. Anyone has any doubts?
How to calculate, sir? Please show one.
So 100 transmissions in a second means what? What is the periodicity? Basically 1 by 100, right? So
That is the frequency.
this is the frequency, transmission per second.
So reverse of that is time period.
Ekdam. So we know how many times it is getting transmitted every second, and we know basically we are trying to compute the percentage bus load for the worst case traffic. So data bytes we know. Why do we add 47? Did you understand that from the lecture material? If you see here, if you count other than this, after data fields, if you count other than data fields, there will be 47 bits considering 7 EOF sizes. Okay. I think I mentioned it somewhere. Yeah. If you count it, you will see there are 47 bytes. So that is why we are adding 47. Now we know how many bytes we have to carry. From that we can compute the number of bits. Now we know there are 47 more bits. Now we know how many bits the message will be of. Now we know how many times in a second from their periodicities, how many times in a second they will be transmitted. Now we can compute that how many bits will be transmitted in a second, and we can add them, right? This makes sense? This computation makes sense? Hello?
Yes.
Okay. If this makes sense, then we know how many bits our bus can carry. How many bits? What does it mean? 125 kilobits per second, right? That is the number of bits that we can carry. If we know that, then we can compute the ratio between them, right?
Yes.
Hold on a sec. My screen is visible, right?
Yes, visible.
Okay. Yeah. So basically, I have to get the ratio between these two, but I have to compute, I have to multiply it with 1.1. Why am I doing that? Why am I multiplying with 1.1? This is explained in the lecture, right? Hello?
Not able to recall.
Not able to recall. You check the lectures. So basically you have to compute the worst case traffic. So total periodic bits you can compute from the overall number of the bits you are getting for all the messages, and you know how many it is possible to carry. So you compute 110% of this the bits that you are going to carry. You increase it by 110%, basically increase by 10%, and you compute the worst case bandwidth. Okay. So in this case you are only having a 7% bus load. Why this 1.1 is coming? See in the lectures. I would like you to ask the same question in the next lecture again. If you have seen the lectures, then this should be explained. Okay. So I wanted to solve another problem though. Anyways, if you solve if you understand how this problem is solved, then you can solve the problems in assignments or in exams actually. So yeah, I'll try to upload this. So today's lecture has been pretty long. I guess you understood what I was trying to say. We'll meet in the next lecture again. Any other questions? I see most of you have left. Anupam, any question?
Medium is wire, only wire, na? The simple wire, what we say, the copper wire.
Yes, insulated copper wires, twisted pair of wires. Okay.
Thank you.
Yeah, so I'm ending the meeting here today. Let's meet in the next week again with new questions. But you tell me from the lecture, why is there a 1.1 multiplied to the bus load? I'll ask you this question again. See you then. Yeah.